All right, we've got to start moving this air parcels around in the atmosphere. We have discussed energy coming into the air, temperatures. We've talked about pressure changes. We've talked about moisture and how it impacts everything. Well, all of that contributes to the motion of the air. So, what do we mean by motion of the air? Well, wind. Have you ever stood outside and just felt the wind in your face, the air blowing in your face? That is air parcels in motion. So, why do they move and how can we forecast where that air parcel hit you in the face is going to wind up 10 minutes later or an hour later? So, let's look at that a little bit. So, what forces control the speed and direction? What do we mean by a force? Force would be, take your car. If you wanted to push your car, it was on a flat surface, and start it rolling in neutral, you and a buddy or however many buddies, and you wanted to push that car, you're applying a force to that car to make it move. Otherwise, it's just going to stay where it is. So that is a force. It is an application of effort to make an air parcel or something move. So the definition of force very simply is mass. So in this case, the weight of the air of your car times the acceleration. So say you go from 0 to 2 miles an hour over the course of 5 minutes. That is an acceleration because you made the car move faster than it was initially going. So that would be how you would calculate a force. So the atmosphere has forces too. It has the air pressure gradient. We've talked about how pressure differences are, what causes them through temperatures, through moisture, divergence aloft, convergence the surface. That is an air pressure gradient. Centripetal force. If you go in a curved, if say you're swinging a weighted rope with even a lasso or whatever, and you see it swinging in a circle, why does it stay in that circle? Because there is something pulling it back, and that rope that somebody's holding onto is holding that rope in place, that circle. That is centripetal force. Coriolis effect doesn't happen anywhere except on a curved surface like in rotating Earth. Friction. Friction is, say you're rubbing along a rough surface, and it's a lot harder to move along a rough surface than if you say you hit ice and you slide very easily. Finally, gravity. Gravity is just the pull of molecules toward each other, and because the Earth is very dense in the middle, everything pulls in towards the Earth. So let's just look at air parcels as far as gradient, pressure gradient. Well, air is always going to flow from high pressure to low pressure. The atmosphere hates a pressure gradient, so it's going to do everything it can to get rid of it. So it is always going to have air moving from that high pressure, nice big high, towards the low pressure. And the closer that gradient is, say you were going down a map, a hillside, and that hillside, very level, very slow slope. All of a sudden, it just dropped off on a cliff. That would be like the tightening of the pressure gradient, your air moving downwards very quickly. Here's the centripetal force. It's always center seeking. As you can see, it always goes back towards one point. It's just what holds that little ball in motion there. Okay, Coriolis effect. This is kind of a strange one, I know. Say you somehow, miraculously, at the same moment in time, you're situated over Canada. 1 hour later, you're situated over the central United States. Well, the Earth rotated, right? So if the Earth rotated, doesn't that mean that the distance covered up here, because the Earth's circumference is much smaller up here, than it is down here is not going to be as far. So there is a force exerted because of that. And in the northern hemisphere, it is a force to the right of the motion. So if an air parcel up here is moving at one speed and the air parcel down here is moving at the same speed, that air parcel down here is having more of a turn to the right because of that Coriolis effect. And you can see all the deflections it makes here. Friction. It can happen at any level in the atmosphere, but it's more prominent near the surface. Say I push the air parcel over a mountain. Well, that mountain's a pretty big block. It's not going to want that parcel of air to move across it. So that is friction, literally. Now, water has very little friction. So the air that's moving across water will move very easily. Now, when it comes to the land, a lot more friction. So, say I'm over Lake Erie. I have air coming in from the lake, moving across the water. Well, the air might be moving 20, 25 miles an hour across the water. It hits the land. Friction is going to slow that air down. Well, what happens when it slows the air down? That air is going to be compressed. It's got to go somewhere. It's going to converge. It can't go into the ground. So where's it going to go? It's going to go upwards in the atmosphere. So that's how you get a lot of a lake effect sometimes in the Great Lakes. Gravity. Gravity is the same all over the Earth. It doesn't change if you're at the North Pole or at the equator. However, because the Earth rotates, you have centripetal force acting as well, so that on a rotating Earth, like we have, you have both gravity, the attraction between the molecules, and the rotation of the Earth holding it in. So you have two components to gravity. Yes, the rotation is, centripetal force is very, very small compared to gravity, but does exist. All these can act to impact the winds. Now, in the vertical, we talked about pressure gradient. Well, on the surface of the Earth, the pressure, might go from 1,000 millibars to 990 millibars over the course of several hundred miles. Maybe in a hurricane, you might get it over a few much less miles, but still, it's not a big pressure change relative to the fact that, say, if you went up in the vertical, 850 millibars is about 5,000 feet up, about a mile up. You drop the pressure 150 millibars in the vertical. So, why in the heck then, since we know that air is going to want to move from high pressure to low pressure, higher pressures at the surface, why do we still have an atmosphere? We have an atmosphere because of gravity. Gravity keeps it in. And the hydrostatic balance is literally gravity balancing the pressure gradient force in the vertical. Well, that is a hydrostatic balance. The air parcel can move. Say a cold front comes along, it's going to push the parcel up, but it's going to move at a constant velocity if it's in hydrostatic balance. Geostrophic wind. Meteorologists love to approximate everything because we cannot solve the equations of motion. So what that means, geostrophic wind is an approximation of parallel winds, basically in the upper atmosphere. You're going to find these when you go above about 5,000 feet, typically. What they are is they're going to flow parallel to the isobars. We just talked about all the pressure gradient and how we want to get rid of high pressure to go to low pressure. Well, what happens is the Coriolis force will balance the pressure gradient force, and we wind up with air parcels moving parallel to the isobars. The longer, the faster that motion is by that air parcel, the faster the Coriolis effect is, till eventually they balance. That is a geostrophic wind. Two forces, Coriolis and pressure gradient. Gradient wind is a circular wind. It moves in a circular motion. Here you have Coriolis effect balanced in the centripetal effect and the pressure gradient, all in balance. And you can get low and high pressure of that as well. As you get close to the Earth, friction plays a role. What does friction do? Friction reduces wind speed. Well, if the wind speed is not as strong, then the Coriolis effect is not as strong. If the Coriolis effect is not as strong, what you wind up with, instead of being parallel to the isobars, is winds will blow outward, away from high pressure towards low pressure some, and inward towards low pressure. So they cross the isobars at an angle. It may not be a very sharp angle, but they do cross it. And here you can see low pressure moving inwards. There's a continuity to the wind. So you can't create a vacuum in the atmosphere. So if you have air converging aloft, what's it doing? It's going to be pushed back down towards the ground. Hits the ground, it's going to spread out, become hard divergence at the ground. Think about high pressure. If you have a high pressure in the atmosphere, the winds aloft are probably converging because you're pushing downwards, you're increasing the pressure at the ground, and then because pressure gradient, you're going to want to get rid of that high pressure. The air is going to flow away. That's where your divergence is coming from. The opposite effect is divergence aloft. Air is going to tend to rise up. Oh yeah, now we're getting storms. Remember, if we rise, pushing air upwards, we're cooling it. We're condensing the moisture. We're forming your clouds. They're all tied together. And here you can see what I just talked about with the winds over a lake. So let's just go quickly. Here, I wanted to show you my house last night. Last night, we had a nice little warm front go through right about here, about midnight. Notice the temperature initially was 50 degrees yesterday, about 5 o'clock in the afternoon. All of a sudden, temperature went all the way up to 70 degrees right in the middle of the night, and then back down. So with that, I wanted to select a graph of wind speed and direction, gust. And we'll go down to that graph now. And you can see right at that warm front went by, winds increased, and I got wind gust up to 40 miles an hour. So there was a pressure gradient that came through with that warm front that caused the winds to increase. They became southwesterly, and we had a very strong pressure gradient force all of a sudden. Here is a map at that time. You can see right here, there's actually low pressure trying to form in Western Virginia at that moment in time. It goes 3 hours later, that low has developed significantly more. It pushed that warm front up through me. But that is what intensified my pressure gradient and intensified my winds. Now that same low, it's up over New England, giving me pretty nice winds down off the mountain slopes. Oh yeah, gravity pulls wind down. So guess what? I am getting wind off the mountains that's being accelerated downward. So if we wanted to look, say, at 300 millibars, notice the parallel winds to the isobar. You have geostrophic winds, very strong across the continental United States right now. 100 knots, 110 knots right here, 120 knots. Here's 130 and 140 knots. So very strong winds from west to east across the United States right now. And if you were looking at upper air sounding, something that's kind of interesting with all of this is how the winds change from above the surface. This was last evening. I hadn't had much wind yet. I had easterly, literally easterly winds before the warm front. But notice the warm front had come in aloft. There's 50 knot southerly winds. So literally 5,000 feet above me yesterday, there was a strong southerly wind, whereas I'm sitting in clouds, rain, and temperatures in 50 degrees. So you can see it literally warmed up as you went aloft because of that warm air being pushed in aloft. That changes the wind direction. You can see how the wind direction then changes with height. So I hope you got a little bit out of this. And, don't hesitate to ask if you have some questions.